All right, so I want to talk a little bit about couple moments because we only briefly touched on it during lecture, and I think you're going to find this information useful, not necessarily required to solve some of the problems, but it's going to make life a little bit easier when you're working on these problems that have what are called force couples. So here we're talking about force couples and the moments that are caused by them. And we have an example problem that we're going to work through. It's example number 3. It's fully worked out in PDF form up on OneNote. And it deals with a beam, a cantilever beam right here. It's supported on the left-hand side and is subjected to two different sets of forces. We have two 200-pound forces that are separated by 1.5 feet. And then we've got two of these forces right here that are unknown, and it's asking us to solve for the value of these forces such that the total moment felt by this beam is equal to 300 pound-feet counterclockwise. And the thing about this problem that can make your life a little bit easier is that it's really just comprised, at least the loading is, of two different what we call force couples. And what you might notice is that these two 200-pound forces and these two unknown forces have something similar with each other in that they are the same magnitude. Both these are F, but they're in opposite directions. This force is going up to the upper right. This force is going to the lower left, and they have the exact same direction. They both have a slope defined by this 3, 4, 5 triangle. So here, these forces are equal and opposite, and they're parallel, and they have some distance between them as well, too. We're not just talking about two forces that are collinear. We're talking about force couples having some perpendicular distance between them. These two 200-pound forces are maybe a little bit easier to understand as a force couple because they're clearly in the same direction. They're both horizontal. The perpendicular distance between them is 1.5 feet, and they are in the opposite direction. So we'd also call that force couple. So when we're dealing with a force couple, a couple things come into play that could make your life a little bit easier. So for example, over here, I'm just going to draw, let's say, a triangle. This is very similar to a homework problem that you have, a right triangle here. So let's say that I have a right triangle and I have a force couple applied to it. So let's say that here we have 100 pounds and we have another 100 pounds, and let's say that these are separated by 10 feet. So in this case, it's clearly a force couple because both of these are parallel to each other. They have equal magnitude but opposite direction, and they have some perpendicular distance between the two of them. So here we have this system is subjected to a force couple. Now the cool thing, or at least the interesting or valuable thing about force couples is that they're going to cause a moment, but calculating that moment is really easy, and then figuring out where it's acting is also relatively easy because there's only kind of one rule. And so here, let's just do a simple exercise first. Let's just sum the moments about this point right here, A, then we'll sum the moments about this point right here, B, and we can even do point C here as well too. So if I were to sum all of the moments about point A, and here I'm essentially making this a free body diagram, so I will draw my coordinate system as well too. If I'm summing the moments about point A and counterclockwise is positive, I'm going to have this 100 pounds right here, but the line of action of the force goes right through point A, and so it has no perpendicular distance. So I can say I have 100 pounds, but its perpendicular distance is 0. All right, so this force here causes no moment about A. Whereas this 100-pound force over here is clearly causing a moment about point A, and its perpendicular distance from its line of action is this horizontal base of the triangle, which is 10 feet. And the sense or the sign of the moment caused by this 100 pounds about A, well, this is going to be causing a clockwise rotation, and we say that counterclockwise is positive. So I would simply get a negative moment due to that 100 pounds. And so I get a total of negative 1,000 pound-feet is the couple moment due to these two forces about A. We call it a couple moment because it's caused by couple forces, but moment, couple moment, the effect, we can call it whichever one we want. All right, so we calculated about A, but now let's go ahead and calculate it about B. If I sum the moments about point B, I'm going to have this 100 pounds has a perpendicular distance of 10 feet and is causing a clockwise rotation about point B, so it'll be a negative moment due to that 100 pounds times 10 feet. And then here, this 100 pounds, the line of action goes right through B, and so even though I have a force, my perpendicular distance is 0 feet. And I get, as a result, negative 1,000 pound-feet. The same exact answer as I get before. And what you're going to find is that when you have a force couple, whether I sum the moments about A, B, C, this point right here, I'll just call it D, or even a point out in the middle of nowhere, we'll call this point omega, it doesn't matter where we take it, we're going to get the same exact moment. And so, for example, let's just say this point omega out in the middle of nowhere, let's say that this distance, I'll put a break line in here, let's say this is another 100 feet out in space. Well, if I were to sum the moments about point omega, because of the nature of couple forces being equal and opposite in force and magnitude and direction, if I sum the moments about point omega, I'll get two non-zero terms where they're going to cancel each other out for the most part, and so I would get this 100-pound force times 110 feet. Again, it'll be clockwise, so it'll be negative, so we get 100 pounds times 110 feet. But then this part of the couple force, this 100 pounds going downwards, that's going to cause a counterclockwise rotation about omega, and so that'll be positive 100 pounds, and its moment arm is simply that 100 feet that's left over. So just a little bit of algebra right here. I'm going to get negative 11,000 pound-feet plus 10,000 pound-feet, and I'll get a net moment of negative 1,000 pound-feet. So the point is that negative 1,000 pound-feet, that is simply done by taking the moment from either one of these points, and really all that you have to do, because one of the terms is going to be 0, just think of the magnitude of a couple moment as equal to the one of the forces times the perpendicular distance in between them. That's all that you need to do to calculate a couple moment, is know the perpendicular distance between them and the magnitude of one of those forces. You multiply them together, that's your magnitude, and then base off whether it's causing a clockwise rotation, which is what it's doing right here, or a counterclockwise rotation. That's what defines the sign of your moment. Okay, so with couple moments, that makes life a little bit easier. I would point out that the couple moment due to a force couple is going to be the same anywhere, and the direction of that moment, just like the direction if we were only looking at one of these forces, because we're in a two-dimensional plane right here, whether my moment is going counterclockwise or clockwise, the axis that they're rotating about is the axis in and out of the screen. If it's a counterclockwise rotation, that means that it's pointing out of the screen in the positive z direction. If it was a clockwise rotation, the sense of the moment would be pushing into the screen, and it would be a negative z direction moment. Okay, so with that in mind, a problem like this, like example 3, that again is fully worked out up on OneNote so you can take a look. A couple different things you can do with this. If you wanted to, because we know with couple moments that I could take the moment about point A, let's call this point A. I could take the moments about point B. I could take the moments about point C or even point D. Anywhere that I take the sum of the moments, I'm going to get the same moment formula. So whichever one is easy, it's up to you. So that's one way that you could do this, is you could sum the moments about A. That means that F right here won't have any moment about A because it's coincident to it. This 200 pounds won't have any moment about point A because it's also along that line. But This force definitely will. Its perpendicular distance is at 1.5 feet. And this force right here, we could break this force up into a vertical component, which is 3/5 of F, and a horizontal component, 4/5 of F. And each of those components will have some perpendicular distance between its line of action and point A. So that's one way that we could do it, but we could also do it by just calculating the couple moment from each of these couples and adding them up together. Either way would work. I'd still want to have this force up here broken up into a horizontal component, which is 4/5 of F, and a vertical component, which is 3/5 of F. And if I do that, I actually kind of break this down into, I'll erase this original force vector right here. Now I've basically broken it down into 3 sets of couple moments. So one of my couple moments is this 3/5 F vertically with this 3/5 F vertically right here, equal and opposite with a parallel distance between them of 4 feet. This 4/5 F is equal and opposite of this 4/5 F, and its parallel distance between them is 1.5 feet. And then finally the two 200-pound couple forces, again, equal and opposite, separated by 1.5 feet. So if I wanted to figure out the total couple moment for the system, I don't even necessarily need to look at a single point to sum everything about. I can just say, well, the moment due to each of these couples is X, Y, and Z, then just add up the results together. So here the entire couple moment, I'm just going to say the sum of all the m naughts, which I'm just calling the couple moments, and again, keeping in mind that counterclockwise is positive, which is our traditional coordinate system and sign convention here. Let's look at the couple moment from the 3/5 F forces couple. And so the magnitude is going to be equal to the force itself, which is 3/5 F, times the perpendicular distance between them, the distance between the, the distance between the two parallel lines, which is 4 feet. And here in this case, these are going to be going in the counterclockwise direction, so that's a positive value. Now the 4/5 F are going in this direction. That means they're going counterclockwise, so it's also a positive 4/5 F. And its perpendicular distance between the two parallel lines is 1.5 feet. And finally, these two 200-pound forces, that couple right there, that is causing a clockwise rotation, so it's a negative 200 pounds times its perpendicular distance, which is 1.5 feet. Now, again, you can take a look at the OneNote solution and the posted information. What's required for this problem is it says, figure out what value of F is required. And again, F was this original force vector right here, which we've decomposed down into an X and a Y. It says what magnitude of F is required to get the entire couple moment for this system to equal 300 pound-feet in the counterclockwise direction. So basically what I'm doing here is I'm saying what value of F on this side will get me 300 pound-feet on this side. So if I simplify things a little bit, here 3 times 4 divided by 5, I'm going to get 12/5 F. Here 4 times 1.5 is 6 divided by 5. I get 6/5 F. And then here I get minus 200 times 1.5, which is minus 300. I can just do a little bit of algebra to isolate F on one side by itself. I'll get 600 equals 18/5 F, or in other words, F equals 5/18 times 600, which is equal to 166.7 pound-feet. That's what the unknown force has to be equal to for the total resultant couple moment on this system to be equal to 300 pound-feet in a counterclockwise direction.